So, hello. My name is Demis Julinic, and I got into programming when I was 12. First, I started with some kind of simple algorithm and data structure competitions. Later on, I ran university. I did my internship at Facebook. I did some bioinformatics research for 2 years, doing deep learning. I've been doing cryptocurrency real-time trading with Go for 2 years at a startup. And nowadays, I'm a DevOps engineer at a Croatian company called Kraken Systems. This company does DevOps, Kubernetes, microservice consulting, and it's also building its own IoT middleware for collecting data from IoT devices, aggregating them, and displaying to stakeholders. So this is briefly about me. But throughout my life, I've been interested in how things work beneath the hood. That's why I chose this topic of how Go data arrays detector works beneath the covers. So let's start with a simple example. We have a counter. So this is some kind of fancy global variable. We count the number of events. This is the number of matches, number of likes, number of sold products, doesn't matter. The main point is we have some kind of function which increments this. And we do it concurrently. So multiple coroutines increment this counter in parallel. However, since this increment operation is not atomic, that is, you load a variable, load a global variable, increment it in store, you could have some kind of nasty stuff. So this output, which we print a count, could be 10,000, which is the expected result, or it could be 5,000, 7,000, 3,000, whatever. It's some kind of observable non-determinism. So something we definitely don't want in our code. So but it's not only 2 examples. There are some famous examples of race conditions in the wild. One of those is called the recall. It's kind of recent-ish. It's a race condition in Linux kernel. More specifically, it's memory management subsystem. And as a consequence, you, as unprivileged user, can gain root permission on the system. Another one is even more deadlier. It's called Terak-25, which is a radiotherapy machine from the earlier century. It had 2 modes of operation, low radiation and high radiation. However, if an operator made a mistake, so it put machine to the 1 setting, and he went to change the machine into 2nd setting, and he did it too quickly, for example, within 8 seconds, the machine would end up in 1 state, for example, high radiation, while the display, so the display the operator saw was the state of the machine, will display a low radiation state. And as such, it has led to multiple accidents, 6 and more, and it led to 2 or more deaths because of this race condition. Okay. Now, before continuing, we need to agree on some definitions. So first, what is a race condition? Race condition is some undesirable effect you can observe when you have 2 or more events happening concurrently, which need to happen in specific order. But this definition is kind of broad because correct behavior is really depending on your domain. So for the rest of this presentation, we are focusing on a subset of it called data races, which have much more clearer definition. Basically, a data race is a concurrent access to the same memory location, one of which is a write. So concurrent access is one where event ordering isn't known. There is no happens before relation between a write and a read, for example. So this thing happens before, it needs a bit of more explanation. So in this slide, we have 2 Go routines. They do happily in their own world. Here is 1 event, here is a 2nd event, so this could be 1 instruction, for example, load a variable. This could be a 2nd instruction, doesn't matter. Since there is no synchronization between 1st and 2nd Go routines, there is no ordering between them. There's no happens before relation. However, as soon as you introduce some synchronization, so either Go's channel sending and channel receiving, or mutex unlocking and locking, we can be certain that this event here happened strictly after this one here, or this event here happened before this one. So let's cover briefly 3 the most typical examples of data races you could encounter in your code base. The first one is racing on the loop counter. We have some normal ordinary for loop we make an anonymous Go routine, and we print a variable I. However, this could print 00055, or this could print 01234, because this I is grabbed from the closure. The main Go routine concurrently changes this variable I, and these 5 Go routines are using the same variable I as a closure. The solution is quite simple. We just copy the variable. It's not a big deal. The second example is similar to the beginning. We have unprotected global variable, which we access concurrently with at least one write. The solution? Put a lock on it, either by using a mutex, or another option is do an atomic operation. This might seem like there's no magic lock happening, but there is a lock on more basic hardware level. So this operation actually locks the whole cache line for single CPU access underneath the covers. So there is a locking even here. You just don't see it in code as clearly. And the third thing is violating the Go memory model. So the Go memory model says, within a single Go routine, the execution happens as if it's happening in program order. Between Go routines, you need to synchronize. So in this example, we call some function setup. Doesn't matter, in a separate Go routine, which sets up the variable A and a public variable boolean done. However, there is no synchronization between this Go routine setup and our main Go routine. So the compiler is free to optimize this for loop away. So it can extract like load a variable done once and do an infinite loop if it's false. That's like perfectly valid Go compiler optimization it can do, and you will end up with a bad code, which has really nasty kind of bugs. So in Go, we have mostly these kind of synchronization primitives you can use. You can use a sync package with its mutex and atomics, or you can use channels. Those are your options, and those are pretty stable synchronization primitives. You should not try to implement your own unless you have really good reason to. Now, let's go more into how this data races is actually detected. For using it, you just add -race flag. So you can run your tests with race detector on, and if any test has data race in it, it will fail. Or you could build or install your binary with data race detector on. And during the runtime, if it encounters a data race, it will print like a big stack trace, which Go routine performed the write, and which Go routine performed another concurrent memory access to the memory location with the full stack trace of how it got there. And underneath the covers, it's using some algorithm called Thread Sanitizer version 2. It's a battle-proven library, part of the LLVM toolchain, which has detected multiple bugs in Go standard library, in Google Chrome, and various other C, C++, Rust, and Go projects. However, it's not cheap. You can expect a runtime slowdown of 2 to 20 times, and bigger memory consumption of 5 to 10 times. And furthermore, it requires a SIGO, and it requires a 60-bit operating system. However, the biggest pro of this library is there are no false positives. So if this tool says you have a data race, there is no like maybe the tool is wrong. You have a data race. And this is a tool you can trust that it will detect it. If it says it's data race, you don't have to like second guess yourself. So how it works? This is like the normal ordinary Go code, Go compiler. We have some function which increments an integer. This is the assembly that is generated. Simple, obvious, Go intermediate assembly. However, as soon as we turn on -race flag, our compiler goes a bit crazy. It emits a bunch of code. This most important stuff being these two function calls. That is a read and a write memory barrier. So before each access to memory location, Go calls this runtime race read or race write and notifies our race detector this event happened, this read or write event happen. So, how does it even know if there is a data race? How do you solve this problem? First, some bad news. The solution is NP hard, sorry. Therefore, every algorithm in this space of detecting data races has some trade-offs in it to make it even feasible for use in everyday life. Now, the first choice is, do we want to have our own code statically analyzed? That we use some kind of annotations on our source code, some kind of special instructions, etc. Or we want to use dynamic analysis, choices being on the fly as the program runs, or we collect all the events and analyze them post-mortem. Golang uses this option on the fly, because for static analysis, you still have a problem of exponential blowup, and you need to do a lot of manual work as a programmer, which takes time and energy. By using this approach with dynamic analysis on the fly, you just have to turn it on. There's no more work required from you. So how it works? As we saw, there is pure happens before data race detectors. There are logset-based ones, which have like a virtual mutex on every manual location. And there are some hybrid approaches. This one is pure happens before. So how does it work? The pure happens before data race detector. It uses a concept called vector clocks. So each coroutine has a vector clock of its current time. So this is a coroutine 1, and I just track my own logical clock, which I increment by 1 on each meaningful operation. This is my second coroutine. I have my own vector clock, which I increment by 1 or each meaningful operation. As you can see, it's a 0 for the second coroutine, is a 0 for the second coroutine. However, as soon as some synchronization happens, for example, mutex unlocking or locking, we establish a happens before relation. And we take this vector clock and this vector clock and maximize it. And the set of all vector clocks, they form a partially ordered set. We can easily compare them. If one is strictly greater than the other, this we have as happens before arc. If we have a situation like this, where neither one is strictly greater than the other, that is a concurrent event. On one execution, it will happen in one order, rather than another, it will happen into another order. That is, we have some kind of non-determinism in our code, in our execution. So this is the first algorithm which exploits these properties. It's called DGIT+. We remember the full vector clocks for each coroutine. We remember the vector clock. When was the last time this memory location X written by coroutine? And when was the last time it was read by coroutine? And we also remember the time this lock, some lock M, was released. So this is our setup for the beginning. Now comes the algorithm. We have our first coroutine, our second coroutine, or coroutine 1. We have some lock M, and we have some memory location X we write to. Each row presents one event. So this is as our data race detector, this state machine, sees it. So at first, it gets an event, okay, coroutine 0 wrote to location X. As I write it, I just update this vector clock for last write on location X. Nothing more. Then coroutine 0 unlocks a mutex on M. This causes it to update the last time coroutine unlocked the mutex M. So we have 4, 0 because our local time is 4. Same here, 4, 4. Sometime later, a coroutine 1 locks the mutex or acquires it. Its own local vector clock is 08. However, after unlocking this mutex, we establish a happens before relation between those two events. Therefore, our own vector clock now becomes 48, which we can easily gain by using per element maximum between 08 and 48. We perform a write, 48, remember 48. And we can do a check here if this write is concurrent to the last write to memory location X. This is the happy path. Without synchronization, there is no happens before arch here, and we are left with 40 here, 08 here. And as soon as we try to write to this memory location X with our own vector clock 02, it's concurrent to the vector clock 40, which was the last write to this memory location, and we have a race. So this is the most critical part of the entire presentation. This is the basic algorithm of how it does it. The rest are just improvements. So just slowly beginning. Write, we update the vector clock for the last write, lock a mutex, unlock a mutex, update the time the mutex was unlocked, we lock it by another go routine, we do pair maximum between our own vector clock and mutex vector clock, we perform a write, we compare, are those two events concurrent. That's the basic algorithm. Now we go to fast track. It's a first improvement on it. Because in our previous approach, we had to remember the full vector clock for each memory location X. That is, the size of the vector clock grows linearly with the number of go routines. If you have 10,000, 100,000 of a million go routines, you would pretty much run out of memory, like not what you want. So they made a really cute observation. If there is no data races in your code, all the writes happen sequentially. And therefore, you need to remember two things for each write. You need to remember which go routine performed the write, so go routine 0 or go routine 1, and when was the write performed in a logical clock of that go routine. So same example as before. Instead of remembering 00, 40, 40, 40, 48, we just remember, here is our nil. The go routine 0 performed the write at local time 4, at its own logical clock 4. Nothing, nothing. And we have another sequential write that happened strictly after the previous write by go routine 1 with its own logical clock of 8. With this approach, we saved a lot of memory because we just have to remember a constant space per each memory location X, irrespective of the number of go routines. For reads, we can use the same trick until we have multiple concurrent reads. Because multiple concurrent reads is a valid approach, we don't insist they happen sequentially, we can fall back to full vector clock. And now we come to the last improvement, which is called this thread sanitizer version 2. They do the following. They split the memory in 8-byte chunks. Okay. So this thing here is usually called shadow word. They make 4 shadow words per each 8-byte chunk. This 4 shadow word pool is memory mapped. So in process virtual address space, you can easily have your own process memory, and there is a memory mapped region for shadow word pool, which gains you constant time access to all shadow words for some 8-byte memory location. You don't have to have any kind of fancy hash maps or anything else. You still keep the full vector clocks for go routines and for locks. Okay. And in each shadow word, there are 4 of them. You remember which go routine was it, what was its local logical clock, which subsection of this 8-byte chunk was written to or read to, or was it a read or a write. In this example, we just write the first 2 bytes of this 8-byte chunk, which are on vector clock 1000. Next iteration, we read from the last 4 bytes, so this is 4 to 8, read. We have on vector clock 520, which is go routine 2, we perform a read. And now we have some kind of race, because our go routine 3 has a vector clock of 5040, and we perform a read on first 4 bytes. But this vector clock is concurrent to the first shadow word. Therefore, we found a race in our code base. Okay. So now we see how Go data race detector works under the hood. We saw what was the most common mistakes, and we saw how we can use it. Now I want to just keep in mind, this tool is not panacea. For example, this code here, you can trick the Go data race detector to not emit any errors, because this code is perfectly valid. But you will probably encounter the same problem as you before. You will have a data race, just the data race detector won't scream at you. So now I'm open for questions, and I have a bit of appendixes for most common questions if there's no particular questions for now.
Thank you. So the questions. Yes, we have the question.
Thank you very much for your talk. Is there any way to disable race detector for performance reasons?
Can you repeat the question?
Is there any way to disable race detector for performance reasons?
I mean, you can compile your binary without race detector included.
Yep.
Because by default, it's not enabled because it is expensive. After you use -race flag, the binary is compiled with race detector support included. But if you mean during the runtime, if you want to enable it or disable it during the runtime, no, there is no option for that.
Okay, I see, thank you.
Thank you very much for your
Oh, sorry.
Yes, thanks. As far as I know, there is limitation for race detector. It's limited with about 8,000 of coroutines. So it's not possible to test programs that run more than 8,000 coroutines. Is it true for now, or was it this limitation existed only in previous versions of Go?
I mean, if you think about it, for each Go routine, you need to remember the full vector clock. So n Go routines, n vector clocks, n squared. 8,000 squared is quite a big number. If you push it more, you will just explode the whole memory space. So that's why it's this kind of rule of the thumb limitation of 8,000 Go routines.
Next question. You've talked a bit about dynamic runtime race detection.
Okay.
Is there any work on static analysis?
There is a bunch of academic paperworks how to do it.
Mm-hmm.
So yeah, there is a lot of know-how how to do it, but at the end you still have a problem. You need to somehow manually specify what's possible and what's valid in your program, and you need to annotate it somehow. So it's quite a lot of work, and it requires quite specialized knowledge. If you want to read more, maybe you could do something like TLA Plus from Leslie Lamport, and his own later works with Calc Plus. He has a great tutorial on his website about these techniques, so you might want to check it out.
Mm-hmm. No practical programs yet, just a bunch of papers, as I get.
With Go, no.
Okay.
With Java, I know I used something 3 years ago for school. I think it was called Pathfinder or something like that. Basically, you had a Java code, you did some special annotations in Java code, and it performed some kind of static analysis on your code in Java. But nothing such as implemented in Go.
Okay, thank you very much.
Hi, thank you for the presentation. So you said that there is no false positive in race detector.
That's true.
But could you provide an example where race detector could not detect race condition?
Well, if you see, so the problem is here. Okay, never mind. The slides are gone. You have a pretty small shadow word pool. You remember only 4 shadow words per each memory location. So when this buffer is full, you do random eviction. So if you have a case when you have some memory location X which is read a bunch of times and written rarely, you might not catch it. But as you run your program with more and more time with this algorithm, the probability you won't catch it diminishes. The other thing you won't catch, if you have a race detector, but events are spaced out quite a bit in time. For example, I access this memory location X now and access it again an hour later. You would probably not really catch it. And sometimes during your next execution, this space out could be 1 minute, 1 second, and it will trigger a data race. So those two are like some kind of edge conditions.
Thanks for the interesting topic, and I wanted to ask, are there any hints to tell the Go race detector that I have 2 memory spaces that can be concurrently accessed or concurrently wrote, and I want to test only them? Are there any features like that in Go race detector, or are there any works, do you know, to provide this functionality?
Just a second. Okay. Okay, never mind. So as far as I know, you cannot really easily mark this is safe for a detector. If you look at the Go standard library, it has a special checks. If the race detector is on, emit this code. If it's off, emit this code. But that's part of the standard library. For your own user space code, so you use the standard library, there is not an easy way to do it. You could maybe do unsafe and write Go intermediate assembly, because the Go data race detector doesn't work on intermediate assembly. It cannot really easily parse it. So that's one way to go around it. Outside for that, not really.
Thanks.
Is there a way to increase numbers of these shadow words? So let's say I have a lot of memory and time, and I want to run check once in a while that will catch more race detector race conditions.
Okay. No. Okay,
Thanks.
there is a way. You compile it yourself.
What?
You compile it yourself.
Go?
No, there is Go uses LLVM shared library, which embeds all this stuff. And in LLVM, you can choose either 1, 2, 4, or 8 shadow words per each memory location. The default is 4, and Go uses this 4. You can recompile the Go binary, the whole Go toolchain, with another LLVM shared library, which uses 8 shadow words per each memory location.
What is the name of library again?
LLVM.
Thanks.
It's like big compiler thing.
Thanks.
So, do we have any other questions? So now and then you have to pick one favorite and just
I think it was this one
present the
about
gopher.
the number of Go routines. Okay.
Yay! Thank you so much.